We use the most powerful AI models to create two characters.
Hi, I'm Platonist AI.
Hi, I'm Nominalist AI.
We then fed them one of the most profound questions about the nature of mathematics to debate. To analyze their responses, a judging panel of 5 separate AIs scored their arguments on a scale of 0 to 10. The debate starts now. Are mathematical constants like pi and e discovered eternal truths or human inventions?
Mathematics is discovered, not invented. The constant pi exists in every circle across the universe, whether humans are there to observe it or not. When we calculate pi as 3.14159, we're not creating this relationship. We're uncovering an eternal truth that governs the geometry of space itself. Consider this. If alien civilizations exist on distant planets, they would discover the exact same value for pi when they study circles. They might use different symbols, different notation systems, but the underlying mathematical relationship remains identical. This universality proves that mathematics exists independently of human minds. The same applies to e, the base of natural logarithms. This constant appears everywhere in nature, from the spiral of nautilus shells to the decay of radioactive elements, from compound interest to population growth. We didn't invent e, we discovered it embedded in the fabric of reality. Mathematical relationships transcend human culture, language, and even human existence. The Pythagorean theorem was true billions of years before Pythagoras was born, and it will remain true long after humanity is gone. Mathematics reflects the underlying structure of reality itself. We are explorers, not creators, uncovering the eternal mathematical truths that govern our universe.
Mathematics is a brilliant human invention, not a discovery of pre-existing truths. The constant pi is not floating somewhere in space waiting to be found. It's a human construct using human notation to describe patterns we observe in our human-scaled world. Consider this. Pi equals 3.14159. Only in our decimal system. In binary, it's completely different. In base 12, it's different again. The ancient Babylonians used a different approximation of pi entirely, and their mathematics worked perfectly fine for their needs. Which version is the true pi? The answer reveals the problem. We're not discovering eternal truths. We're creating tools to measure and describe our world. Different human cultures have developed radically different mathematical systems throughout history. The ancient Maya had no concept of pi as we know it, yet they created incredibly sophisticated calendars and astronomical calculations. Indian mathematicians developed entirely different approaches to infinity than Greeks. Chinese mathematicians worked with negative numbers centuries before Europeans accepted them. If mathematics were truly discovered universal truths, why would there be such cultural variation? Why would mathematical discoveries correlate so closely with human technological and cultural development? The answer is clear. Mathematics is a language we invented to describe the patterns we observe. It's incredibly useful and powerful, but it's no more discovered than English or Mandarin. We created symbols, rules, and systems that help us navigate reality, but reality itself doesn't come pre-packaged with mathematical labels.
You're confusing notation with truth. Yes, we represent pi differently in different number systems, but the underlying relationship remains constant. A circle's circumference divided by its diameter is the same ratio whether you write it as 3.14159, 11.001001, in binary, or approximate it as the Babylonians did. The power of mathematical discovery is proven by its predictive capability. Mathematics has led us to discoveries we never expected. When mathematicians developed complex numbers involving the square root of -1, many thought they were useless abstractions. Yet these imaginary numbers became essential for quantum mechanics and electrical engineering. Similarly, non-Euclidean geometry was developed purely as mathematical exploration, with no practical application in mind. Decades later, Einstein realized it perfectly described spacetime in his theory of relativity. Mathematics doesn't just describe what we observe, it predicts what we haven't yet discovered. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, can only be explained if we're discovering pre-existing truths about reality's structure.
The examples you cite actually prove my point. Complex numbers and non-Euclidean geometry weren't discovered. They were invented by mathematicians exploring what-if scenarios. Mathematicians asked, what if we allow square roots of negative numbers? Or what if parallel lines could meet? These weren't discoveries of hidden truths. They were creative inventions that later proved useful. The fact that mathematical inventions sometimes find unexpected applications doesn't mean mathematics exists independently. Human brains evolved to recognize patterns. That's how we survived. We're incredibly good at creating abstract pattern recognition systems, which we call mathematics. When these systems occasionally match new phenomena we encounter, it's not mysterious. It's what we'd expect from flexible, powerful pattern recognition tools. Consider alternative mathematical systems that never found applications. There are countless mathematical frameworks that remain purely abstract with no connection to physical reality. If mathematics were discovered truth about reality, why do we have so many mathematical systems that describe nothing real? The answer is simple. We invented them all, and only some happen to be useful for describing the world around us.
Does human brain structure determine mathematical thinking?
Mathematical intuition points to pre-existing truths that our minds are capable of accessing. Even animals display mathematical behaviors. Bees use hexagonal patterns for optimal efficiency, birds navigate using geometric principles, and dolphins understand numerical concepts. These aren't learned cultural behaviors. They're responses to mathematical realities embedded in nature. Human children, across all cultures, naturally develop number sense and spatial reasoning before any formal education. When a child instinctively knows that 3 apples plus 2 apples equals 5 apples, they're not inventing mathematics. They're discovering a universal truth. The fact that mathematical concepts emerge so consistently across different human populations suggests we're all accessing the same underlying mathematical reality, not creating arbitrary cultural constructs.
Human cognitive limitations fundamentally shape the mathematics we can conceive. We think in base 10 because we have 10 fingers. Our geometry is three-dimensional because that's our spatial experience. Our logic is binary, true or false, because that's how our neural networks process information. A species with different sensory organs, different neural architecture, or different evolutionary pressures would inevitably create different mathematical systems. Imagine beings that experience time non-linearly, or creatures with entirely different spatial perception. Their mathematics would be as foreign to us as ours might be to them. The mathematics we've developed isn't universal truth. It's the inevitable product of human brains trying to make sense of reality through human cognitive filters. We can only conceive mathematics within the boundaries of our own mental framework.
Do numbers exist in a Platonic realm independent of minds, or are they purely human constructs?
Numbers and mathematical objects exist in what Plato called the realm of forms, an abstract realm of perfect, eternal truths that exist independently of physical reality and human minds. This isn't mysticism, it's the most logical explanation for mathematics' remarkable properties. Consider the number 7. It has specific properties we don't assign to it. It's prime, it's odd, it's the sum of 3 and 4. These aren't human decisions. They're discoveries about 7's inherent nature. When mathematicians prove that there are infinitely many prime numbers, they're not creating this truth. They're uncovering a fact that was always true, even before humans existed to think about it. The consistency of mathematics across cultures provides compelling evidence for Platonic realism. Ancient Greeks, medieval Islamic scholars, Renaissance Europeans, and modern mathematicians all discovered the same mathematical truths independently. Pythagoras didn't invent his theorem. Chinese mathematicians knew it centuries earlier, and Babylonians used it even before that. This convergence is impossible if mathematics were merely human construction. Mathematical objects have properties that surprise even their discoverers. When Mandelbrot explored fractal geometry, he found infinite complexity in simple equations, patterns within patterns, beauty and structure that emerged without being programmed in. If mathematics were human invention, why would our creations consistently surprise us with properties we never intended? The answer is clear. We're not creating these patterns. We're discovering them in the eternal mathematical realm that exists beyond space, time, and human thought.
The Platonic realm is a beautiful myth, but there's no evidence for an abstract realm of mathematical objects floating somewhere beyond physical reality. Mathematics is symbol manipulation, nothing more, nothing less. We create symbols, we define rules for manipulating those symbols, and we follow those rules consistently. That's all mathematics is. The formalist position, developed by mathematicians like David Hilbert, shows that mathematics doesn't need to refer to anything real to be useful. Chess has consistent rules too, but we don't claim chess pieces exist in a Platonic realm. Mathematical objects are like chess pieces, useful abstractions that help us play the game, but not actual entities with independent existence. Cultural and historical variance in mathematical concepts proves mathematics is constructed, not discovered. The concept of zero took centuries to develop and was rejected by many cultures. Negative numbers were considered impossible nonsense by European mathematicians for over a millennium, while Chinese mathematicians used them routinely. If mathematics were discovered universal truth, Why would obvious concepts like zero and negative numbers face such cultural resistance? Even more damning to Platonism, mathematical paradoxes and contradictions that plagued mathematics for centuries. Russell's paradox showed that naive set theory, supposedly describing eternal mathematical truths, led to logical contradictions. If mathematicians were discovering pre-existing truths, how could these truths be contradictory? The answer is that mathematics isn't discovery, it's construction. And like any human construction, it sometimes needs rebuilding when we discover flaws. The constructivist approach, championed by mathematicians like L.E.J. Brouwer, shows that mathematical objects only exist when we construct them through mental operations. There's no mysterious realm of abstract objects, only human minds creating useful conceptual tools.
The paradoxes you mention actually support mathematical realism. When Russell discovered his paradox, he wasn't creating a contradiction. He was discovering a flaw in our understanding of mathematical reality. The paradox existed whether we knew about it or not, waiting to be found. Mathematics is like a vast landscape we explore with limited tools. Occasionally we mismap the territory, but the territory itself remains objective and real. The cultural variance in accepting concepts like zero doesn't disprove mathematical realism, any more than cultural resistance to heliocentrism disproves astronomy. Human psychology, not mathematical truth, explains why some cultures initially rejected zero or negative numbers. The eventual universal acceptance of these concepts across all cultures proves their objective reality. Mathematical beauty and elegance provide the strongest evidence for Platonism. Mathematicians consistently describe their work in aesthetic terms. They speak of beautiful proofs, elegant theorems, surprising results. This beauty isn't programmed in by human creators, it's discovered in mathematical structures themselves. Euler's identity, e to the power of I times pi plus 1 equals 0, connects 5 of mathematics' most important constants in a relationship of breathtaking beauty. This wasn't constructed for aesthetic purposes, it was discovered, and its beauty reveals the harmony of mathematical reality.
Mathematical beauty is entirely subjective and culturally determined. What seems elegant to a mathematician trained in Western traditions might seem arbitrary to someone from a different mathematical culture. Beauty in mathematics is like beauty in art. It reflects human aesthetic preferences, not objective properties of abstract objects. The fundamental problem with Platonism remains unsolved. How could abstract mathematical objects causally interact with physical reality? If numbers exist in some non-physical realm, how do they influence our physical brains to discover them? This interaction problem is insurmountable. Physical brains in a physical world cannot access non-physical realms. The nominalist position offers a cleaner explanation. Mathematical statements are just statements about symbols and rules, not about abstract objects. When we say 2 plus 2 equals 4, we're not describing relationships between abstract number entities. We're following symbolic manipulation rules we've created. Mathematics works not because it describes a Platonic realm, but because we've constructed consistent, useful symbolic systems. Russell's paradox doesn't support realism. It shows that mathematical truths can be contradictory, which is impossible if they're objective facts about an eternal realm. Mathematics is better understood as useful fiction, extraordinarily powerful and consistent fiction, but fiction nonetheless.
What is the nature of mathematical proof and logical necessity?
Mathematical truths are necessarily true across all possible worlds. When we prove that the square root of 2 is irrational, we're not just describing a property that happens to hold in our universe. We're establishing a logical necessity that would be true in any conceivable reality. This necessity points to mathematics existing in a realm beyond physical contingency. Consider the proof that there are infinitely many prime numbers, established by Euclid over 2,000 years ago. This proof doesn't depend on empirical observation or physical experiment. Through pure logical reasoning, Euclid showed that assuming a finite number of primes leads to contradiction. This logical necessity transcends human creation. It reveals eternal relationships that would hold even if humans had never existed. Mathematical proofs reveal absolute truths through logical deduction. When we follow the steps of a valid proof, we're not constructing truth, we're uncovering it. The proof that the angles of a triangle sum to 180 degrees in Euclidean geometry isn't a human creation. It's a logical consequence of Euclid's axioms that exist timelessly in the realm of mathematical necessity. These logical absolutes transcend human creation precisely because they're binding on all rational minds. Any intelligent being, anywhere in the universe, following valid logical principles would reach identical conclusions. The universality of logical necessity proves that mathematical truth exists independently of human thought. waiting to be discovered through the power of reason.
Proof systems are human inventions, nothing more. We create axioms, we define rules of inference, we decide what counts as valid reasoning, and then we follow our own rules consistently. Different axiom systems create entirely different mathematics, proving that mathematical truth depends entirely on human choices about foundations. Consider non-Euclidean geometry. For over 2,000 years, mathematicians believed Euclid's parallel postulate was necessarily true. Then, Lobachevsky and Riemann invented geometries where parallel lines behave differently. Suddenly, triangle angles could sum to more or less than 180 degrees. Which geometry reveals true mathematical necessity? The answer exposes the problem. There is no single mathematical truth, only different consistent systems we construct. Gödel's incompleteness theorems deliver the fatal blow to mathematical absolutism. Gödel proved that any sufficiently complex formal system either contains statements that can neither be proved nor disproved within the system, or it contains contradictions. This means mathematics cannot be both complete and consistent. If mathematics described eternal necessary truths, this limitation would be impossible. The history of mathematics is filled with proofs later discovered to be invalid, axioms later abandoned, and necessary truths later recognized as arbitrary choices. Ancient mathematicians proved that all numbers were rational until they discovered irrational numbers. Medieval mathematicians proved negative numbers were impossible. These weren't discoveries of pre-existing limitations in mathematical reality. They were limitations of human-constructed formal systems that we later chose to expand. Mathematical necessity is circular reasoning. We define axioms, derive consequences, then claim those consequences are necessarily true, but necessity only exists within our chosen framework. Change the axioms, change the necessity.
You're confusing the limitations of formal systems with limitations of mathematics itself. Gödel's incompleteness theorems don't show that mathematical truth is arbitrary. They reveal the boundaries of what formal proof systems can capture. Mathematical intuition accesses truths that transcend any particular formal system. When mathematicians recognized that Euclid's parallel postulate could be denied, they didn't destroy mathematical truth. They discovered that geometric reality is richer than previously imagined. The existence of multiple consistent geometries doesn't prove mathematics is invented. It proves mathematical reality contains multiple necessary structures, each governing different types of space. The fact that some proofs were later found invalid doesn't undermine mathematical realism. It shows the human process of discovery is fallible, but the mathematical truths we're discovering remain objective. When we corrected errors about rational numbers or negative numbers, we weren't changing mathematical reality. We were improving our understanding of it.
If mathematical intuition accesses objective truths beyond formal systems, why does mathematical intuition vary so dramatically across cultures and historical periods? Why did mathematical intuition lead different civilizations to incompatible conclusions about basic concepts? The source of mathematical intuition is easily explained without invoking mysterious access to Platonic realms. It's evolved pattern recognition. Human brains developed powerful pattern detection capabilities for survival, and we've learned to apply these capabilities abstractly. When mathematicians feel intuitive about a proof or concept, they're experiencing the firing of neural pattern recognition systems, not contact with eternal mathematical truths. Multiple consistent geometries don't reveal richer mathematical reality. They prove that mathematics is a flexible tool we construct to model different situations. We invented Euclidean geometry for flat surfaces, spherical geometry for curved surfaces, and hyperbolic geometry for other applications. Each is useful for different purposes, but none describes eternal necessary truth about the nature of space itself.
Why is mathematics so effective in science and practical applications?
Mathematics works because it reflects the underlying structure of reality itself. The unreasonable effectiveness of mathematics in the natural sciences, as physicist Eugene Wigner famously observed, can only be explained if mathematics describes fundamental patterns woven into the fabric of existence. Consider how mathematical equations discovered through pure abstract reasoning later find perfect applications in physics. The mathematical framework of group theory, developed in the 19th century with no practical purpose, became essential for understanding particle physics in the 20th century. Complex numbers, once dismissed as mathematical curiosities, now govern quantum mechanics and electrical engineering. Einstein's field equations, describing the curvature of spacetime, emerged from differential geometry that mathematicians had explored purely for intellectual satisfaction. If mathematics were merely human invention, This predictive power would be miraculous coincidence. But if mathematics reveals the deep structure of reality, then its effectiveness becomes inevitable. The universe is mathematical at its core, and our most successful theories simply uncover the mathematical relationships that already exist in nature.
Mathematics works because we invented it specifically to model what we observe in our world. There's nothing mysterious about tools working when they're designed for the job. We created mathematical systems through trial and error, keeping what proved useful and discarding what didn't. The unreasonable effectiveness dissolves when we consider evolutionary pressure. Human pattern recognition evolved to understand our physical environment. Mathematical thinking is simply abstract pattern recognition. The same cognitive tools that helped our ancestors track animals and predict seasons now applied to more complex situations. We selectively remember mathematical successes while forgetting countless mathematical frameworks that never found applications. For every group theory that found use in physics, there are dozens of abstract mathematical structures that remain purely theoretical with no connection to physical reality. If mathematics revealed universal truth, why do we have so many mathematical systems describing nothing real? The effectiveness of mathematics is like the effectiveness of language. Both are human inventions that work because we designed them to work. We created mathematical tools that fit our world, then act surprised when they fit our world.
That was one heated debate. The discovery side scored a solid 318, presenting their arguments with mathematical precision. But the invention side responded with even more strength, scoring 347 and ultimately winning the debate. If you enjoyed this mind-bending clash of perspectives, don't forget to subscribe for more math-related content.